Hello and welcome. In this video lesson we are going to take a look at the idea of Nullclines. And Nullclines are a way for us to better understand what's going on in the phase plane of a nonlinear system of differential equations. In particular, one that is homogeneous, one, in other words, that doesn't depend on time but depends only on the values of the dependent variables. That is, the rates only depend on those. So a Lotka-Volterra model, looking at predator-prey populations, is actually a nonlinear system of differential equations. They are first order, but they have no closed form solution. So there's no way to solve for x of t and y of t. But a natural question is, how do we understand how a solution behaves for a given initial condition? So what will it do? Well, we could look at the phase plane, but one of the disadvantages of looking at the phase plane is that the phase plane is not always available. In particular, in our next lesson, when we take a look at a system of three differential equations, it becomes very difficult to try to visualize what is happening in a three-dimensional phase plane. So there are a few ways that we can explore this. We looked at the linearization theorem in a previous lesson, and today we're going to combine that with this qualitative approach. Qualitative just means that it'll help us understand what's happening in the long run, but it may not be very revelatory in terms of telling us what's happening right away. Now, nonlinear models often have multiple equilibrium points. We found this before. And so we'll have to really, before we get into this, look at every single equilibrium point for our system and qualify it or categorize it, classify it as a sink, source, saddle point, spiral sink, spiral source, or center. Now let's go ahead and look at a definition that's going to help us build these nullclines. So what is a nullcline? Well, a nullcline, if you think about that, the word null means zero. Cline is like incline or decline. A nullcline means something that has a zero slope. So it's often a function, and it's the set of all points for which either one differential equation or the other has zero change. So what's the difference between that and the equilibrium point? Well, a nullcline is just the set of values for which only one of them is in equilibrium and the other may not necessarily be. An equilibrium point is where both of the rates are simultaneously zero. So nullcline, where only one of the rates is zero. And then when any points where both of them are at a nullcline means they both have zero rates, and that by definition is then an equilibrium point. So here we've looked at this predator-prey model here. Let's say that we have some sort of competing species here. So we see that in both equations, an interaction between the two species leads to a negative effect on the rate. So they're probably fighting for resources, etc. Now, suppose we do want to create a phase plane in which the horizontal axis measures the number of deer and the vertical axis measures the number of elk. You'll want to record the findings below in a sketch of a phase plane. This sketch will fully describe long-run behaviors and will demystify the phase planes we get when using technology. So we've observed that these phase planes for models like this look pretty chaotic, and we want to be able to remove that chaos and to understand what's going to be happening. So the first thing I do is locate my equilibrium points. We did this in our previous lesson, along with determining how each of these equilibrium points behaves locally. And so we set both of them equal to 0, use Wolfram alpha to solve. And in this case, we obtained 4 equilibrium points. And using the linearization theorem, we classified 0, 3 as a sink, meaning that we observed that a lot of solutions actually spiraled into, or I shouldn't say spiraled into, but sank into the 0, 3 equilibrium state. 1, 1 was a saddle point, and so a saddle, remember, along one straight line solution, the trajectory gets attracted towards that equilibrium point, but the fact that you have a positive eigenvalue, that sort of kicks it back out. So trajectories not starting at this point can never get there. 2, 0 we classified as a sink. So once again, we observed that certain solutions made their way to that equilibrium point. 0, 0 is a source, so trajectories not starting at this point can never get there. So we have 2 equilibrium points that we've already been able to demystify as solutions just won't get there unless they start there. So the next thing we're going to go ahead and do is find the nullclines of dx dt. by finding all conditions under which dx dt equals 0. And so we do that. So basically we're just going to set one equation equal to 0, and we're going to solve. And as mentioned earlier, these are our two Nullclines. These are actually functions, and these are anytime x equals 0. Now y could be whatever it wants to be, but as long as x is equal to 0, this equation will always, the right-hand side will always be 0. So y could be 50, y could be 100. So this solution, x equals 0, is the vertical line that runs along the y-axis. Y equals 2 minus x, well, that's a line with a vertical intercept of 2 and a slope of -1. So what I want to go ahead and do is I'm going to plot this. I'm going to use a different color because we're going to have a lot of information on this. And so here is my one Nullcline. Okay, that's the, sorry, that's not the Nullcline. The Nullcline is the vertical axis. So we'll go ahead and indicate that we have a Nullcline that runs up and down along this axis right here. And let's give that some thickness. Okay, well, good enough. Now our other line is going to run at a vertical intercept of 2. Minus x will cause that line to go through 0, 2 and 2, 0. So let's see if I can make this happen. Not bad. There we go. And so there are my two Nullclines. Now you see what those Nullclines have done. They have divided up this into essentially 4 regions. And within each of these 4 regions, something interesting is going to happen. Now, the one thing that we do know is that along the green Nullclines, that the dx dt value is 0. So we probably want to write that. So dx dt is equals 0 along both green lines. And those are green Nullclines. And by the way, up here, we could just check. You could see that if you plug in 2 minus x for y here and do some distribution, that will all 0 out. So I encourage you to do that. And so along both green Nullclines, dx dt is 0, which basically means that, remember, dx dt, this guy either points right or has a left pointing component. But if dx dt is 0, that means that vectors in this phase plane that fall along either of these two straight lines do not have a left or right pointing component. So this means that the vectors, the phase plane vectors, or arrows if you want to call them that, the phase plane vectors along the x Nullcline will point strictly up or down. Right, and that's again because of this statement here, dx dt is 0 everywhere along these two green lines, and so you might see that the vectors along these Nullclines either point up or down. Now I'm not going to worry about those right now, but the one thing to note is that even along this green Nullcline, the vectors will either point straight up or they'll point straight down, because of the fact that on that green line, dx dt is 0, so there's no left or right component to that vector. Whereas over here, we may see a vector that has a horizontal and vertical component. Okay, so next what we want to do is within each of these regions, because along these green lines, that's where dx dt is 0, the only way, if you remember from Calc 1, for a derivative to change signs is to pass through a critical point. So you can think about these green lines as representing critical points. So if I look at these 4 regions that we formed here, I'm just going to arbitrarily label them 1, 2, this whole region down here is 3. The axis does not do anything here, only the Nullclines do. So within each of these 4 regions, I may have a different value, a different signed value of dx dt. So what I'm going to do is I'm going to look at, well, what about dx dt in those four intervals? Is dx dt positive, negative, or zeros? This is like the first derivative test in essence. So for region 1, I'm going to pick a point somewhere in region 1. It really doesn't matter because all the dx dt vectors within this region will all point right or they will all point left. And that is because the only way for the arrow to change directions is for me to have a situation where dx dt is 0. Okay, so let's pick a point in there. I'm going to pick the arbitrary point, maybe 2, 2. And so what I'm going to do is plug in 2, 2 into my dx dt equation, which is this guy here. So if I plug in 2 for x, here I'll have 1 minus 2 over 2, which is 0. And then here I'll have negative 2 times 2, which is negative 4. And so that comes out to a negative number. Now, I don't really care that it is negative 4. I just care that it's a negative number. And that means that dx dt is negative, which means, well, what's happening to x? Well, that means x is decreasing. So everywhere in here, all these vectors that I see in this region 1 will have vector components whose horizontal component points left. So you may have a mixture of vectors that point this way and this way, but all we know right now is that all the vectors in region 1 will point left. We'll have a leftward pointing component to the horizontal. Now we'll do the same thing for region 2. Let's pick a point down here. I like the point 1, 0. That looks good to me. It's an easy point to plug in. So if I plug in 1 for x and 0 for y, I'll have 2, 1 minus 1/2. That'll be a positive number. And so you can even see that the signs switched when I jumped over one of the Nullclines. And so since dx dt is positive, so negative means x is decreasing, positive means x is increasing. So within this interval, all the vectors in this portion of the phase plane will have right-facing vectors. And now region 3, I'll pick one over here. I'll pick negative 1, 0. That's an easy point to pick. And if I pick negative 1, 0, I'll plug in negative 1 for x, and you'll see that we'll end up with a negative number. Now you still do have to plug these in. You have to be careful because sometimes, even in Calculus 1, when we have a critical point, it's neither a max nor a min. And like a cubic function, if you remember from Calc 1, x cubed has a critical point at x equals 0, but that point right there is neither a max nor a min. And so that means since the vector at negative 1, 0 points left, all the vectors in this region will point left. We don't know what portion where the vectors will point up or down. We're only analyzing dx dt right now. And region 4, we'll do the same thing. For region 4, we'll have to pick something that's in there. So how about negative 1, 4? I'm pretty confident that point is in there. Negative 1, 4. And if we go ahead and plug that into the dx dt equation, we are going to get a positive number. So that's, again, plugging it in for x here and for y over there. Okay, so that means that within region 4, all of our vectors will point to the right. So right up here, we can say that these vectors will all point to the right. Well, what have we done so far? If we pause for a second and think about what the value of this is, right now we've been able to say, hey, you know what? If you have an initial condition that falls into region 1, the first thing that's going to happen when we press play is that particle or that trajectory is going to move towards the left. It may move left and up, it may move left and down, but all we know is that all these points in here will be moving to the left. All the points in here will be moving to the right. Okay, so that's our Nullcline analysis for the x Nullclines. Now we're going to repeat this for the y Nullclines. So for dy dt, we have to, again, plug in or find our Nullclines for y, and we'll go ahead and do that next. So in this case, we're going to set dy dt equal to 0, and we get, again, two solutions. So anytime y is 0, regardless of what x is. If y is 0, the whole right-hand side will become 0. Now, the y equals 0 is the horizontal line that lies along the x-axis. So we can go ahead and plot that. There's our, I want to use a different color there. Let's go ahead and use this guy here. So there we go. All right, so y equals 0 is one of our nullclines. And then y equals 3 minus 2x, which is the line that goes through 0, 3, and decreases by 2 for every 1 unit of x. So we should have 1, 1. Let's see, which means we'll go through these 2 points here. Close-ish. Good enough, that will work. All right, that's good enough, I think. It's about as accurate as I think I'm going to be able to get it here. There we are. Okay, so that goes through that location. And once again, the thing that we should realize is if we plug in 0 for y, the right-hand side will be 0. If we plug in 3 minus 2x for y, the right-hand side will be 0. So anywhere along the pink Nullcline, dy dt equals 0, everywhere along the, I'll just call them the pink lines. So what does that mean? Well, dy dt, the dy dt of a vector either points up or points down. But if all the vectors on these red lines are equal to, if the vectors have a 0 dy dt component, that means everywhere along these red lines, those vectors can only point left or right. Again, we're not going to worry about that detail right now, but that's an important thing to note. So along pink line, all vectors have only a horizontal component. So that means, once again, just like in our previous example, if you hop over one of the nullclines, like a critical point, the arrow, the dy dt, changes perhaps from pointing down to pointing up. So we're, again, going to quantify all of these regions and pick a point in all of these regions and look at whether dy dt is positive, negative, or negative. So let's take a look at the points in these regions and the rate of change, dy dt. And if we look at, for example, in region 1, we could look at the point 2, 2. That appears to be in region 1. And if I plug in 2 for x and 2 for y in here, I will get, let's see, 2 for x, 2 for y. This will give me 3 times, that's 6. 6 times 1/3 will give me, 6 times 1/3 will give me 2. And this will give me negative 2 times 2 times 2, which is larger negative than this is positive, and therefore the rate of change that I will get will be negative. So that means that in this whole region 1, because 1, 1 is a sample point in there, and because all the points in here lie within the same set of y nullclines, that means that my vectors in here will all have a downward facing component. Now, in region 2, if I pick something like 3, say 3, 1, that looks to be a point in the region, I will get a positive value. I'll let you verify that, which means all the vectors in region 2 will be upward facing. And I'll do the same thing for region 3. In region 3, I could pick, let's say, negative 1, negative 1. And I will get a negative value. I've worked this out already. And so that means all the vectors in region 3, which, by the way, that's everything below these two nullclines. In region 4, I could pick, let's say, negative 1, 1. Or I could even pick 0, 1. 0, 1 would be a little bit easier, but I will get a positive value. And that vector, all the vectors in this region will be pointing up. So what we've just determined is basically that if, depending on where your initial condition is, if your initial condition starts somewhere out here, then the y component of your vector, of your where that object is going to move, its trajectory, it's going to move down, and depending on where it is with respect to the x nullcline, it looks like a point that starts way up here will be moving down and to the left. So it seems like a point that starts up here based on these two nullcline graphs will be vectors that point down and to the left. And what we want to do now is we don't want to have to keep looking back at these two graphs, so we actually want to overlay these on top of one another. So we're going to do that next. So this is a bit of the tricky part, is overlaying these on top of one another. But here I've just copied and pasted, and you can just go ahead and draw over the top of one of these graphs. But these are my x nullclines in green here, with my arrows drawn within each of these four regions. Now I'm further going to subdivide this by taking the y nullclines and also plotting them on the same set of axes. So that means that what I'm going to do here is take this guy, and plot 3 minus 2x on top of this graph that has the x nullclines in it. Or you could do it vice versa, it doesn't really matter. So 3 minus 2x, we said we'll go through 1, 1, and 0, 3. So let's see if I can draw this well. Not really, but we're getting there. Let's see. So this needs to go through 0, 3, and it needs to go through 1, 1. So getting pretty close there. And this doesn't need to be perfect. This is just for illustrative purposes. So here you can see that these two functions intersect at the point 1, 1. Well, that's a y nullcline and an x nullcline intersecting one another, and we said that when y is in a nullcline state and x is in a nullcline state, that's an equilibrium point. And so you'll notice that that is actually one of our equilibrium points. That's the equilibrium point 1, 1 that we obtained right here. Very nice. So it turns out that there is a connection between nullclines and equilibrium points. I just want to adjust this just a little bit because it's kind of bugging me. There we go. That's better. Whoops. Was better. There we go. Battling technology. Okay, there we go. And so I'm also going to plot this second nullcline here. I'm going to go ahead and grab this, or I could just plot it again. And now I'm going to be really careful because now I see that depending on what region we're looking at, everywhere, if I just look at the green nullclines, those are my x nullclines, then I know that everywhere within this compartment, ignore the pink for now, everywhere within this first region, the top right portion, which corresponds to what we came up with up here, everywhere in this top right portion, I'm going to have vectors that point left. So what I'm going to do is I'm going to erase this right here, and I'm going to use green for consistency. And so that means here the vectors will point left. Also here the vectors will point left. And the reason I'm drawing another vector here is because there's a y nullcline, which means when we jump over this nullcline, the upward or downward component of the vectors could change. And that's why I'm drawing another left-facing one here. Also, right in this little pocket here, I'm going to draw a left-facing vector because, again, that's where the flow is in that direction. And then everywhere in this green portion, the vectors are pointing right. So I'm going to erase this guy here and actually just go ahead and draw two right-pointing vectors, one here and then one up here as well. So that all I'm really doing is just kind of populating in those vectors where they need to go. Now everywhere in this portion, the bottom left half, the vectors point left. And so now it's been subdivided into two regions because of the pink vector. So here there's left pointing vector, here there's left pointing vector. And so that covers me everywhere within this region, which corresponds to what we called region 3. So we've just basically labeled the top half and the bottom half. And now also we have this fourth region over here, and the vectors point right everywhere down here, so I'm going to erase this right pointing vector and put it in all of those little pockets. So here, 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 oops, and here as well. Okay, now you're probably guessing, well, what's coming next, and that is to label the vertical component of those vectors. So now we have to focus our attention on the pink lines, and everywhere within pocket 1 of the pink lines, there's going to be downward pointing vectors. So that means everywhere within this region, above this region, we're going to have downward component vectors. So that means here I'm going to have a downward component. That means here, this vector is going to have a downward component. So when you really zoom in there, and that's going to have a downward facing component. Let me go ahead and redraw that. So that'll point right, and then we'll have a downward component there. Now we can go ahead and zoom out a little bit, and that covers us within that region. We also know that within region 2, we're going to have upward pointing vectors. So region 2 is everywhere within the bottom right portion of that. So those are going to be upward pointing vectors. So I'll have an upward pointing component to this guy, and an upward pointing component to that guy. Now within region, what we called region 3, which is everywhere in the bottom left, there's going to be a downward component, pointing component of that vector. So see, that's going to be here, it's going to be a downward facing component, and here, because we're still in the same realm of those two y nullclines. The reason we drew those two green vectors, or those two pink vectors, is because here trajectories flow down into the left. Over in this pocket, trajectories flow down into the right. So that's why we continue breaking these up into further regions. And finally up here, everywhere up here in this top left portion, there's an upward facing component to that vector. So this guy will have an upward facing component, this guy will have an upward facing component, and this guy will have an upward facing component. Also this guy here as well, because again, we're on one side of that nullcline. So let me zoom out a bit, and we've already said that there are 2 equilibrium points, or 4 equilibrium points. There's one there, there's one there, there's one where any 2 different colored lines intersect, so 2, 0, that's another equilibrium point, and 1, 1 is our 4th equilibrium point. Oh, I'm sorry, not 0, 2. 0, 3 is actually an equilibrium point. That's where those 2 nullclines meet, those 2 nullclines meet, those 2 nullclines meet, and those 2 nullclines meet. Now we know that 1, 1 and 0, 0, 1, 1 acts as a saddle, 0, 0 acts as a source. So we know that initial conditions anywhere will never end up at those 2 equilibrium points, but some do end up at 2, 0, and some do end up at 0, 3. So imagine that there's a point inside of here. Where can that point go? Well, that point can only move down and to the right, down and to the left, excuse me. So it can't go up, and it can't go to the right because of how the signs of dx dt and dy dt. So this point is free to move down and to the left. Now, whether it's exaggerated, we can't tell based upon that, but this trajectory can flow this way. But what happens if it bumps into this? Well, that is a y nullcline. That's going to be where the y value is 0, where the rate of change of y is 0. So that means that we see that there's a left component to the vectors on the right side of this y nullcline, and there's a left component to the vector on the left side of this nullcline. But you see that whenever you jump over this pink nullcline, the vectors have an upward facing component, but to the right they have a downward facing component. So it turns out that because dy dt is 0 all the way along this thing, but dx dt is positive, we can see that this point can pass inside of this region, and now we're limited to behavior that is up and to the left. So you can see that one thing that could happen is that point can go into that equilibrium, Another thing that could happen is perhaps maybe it hits one of these walls first. What happens if it hits that? Well, that's an X Nullcline. An X Nullcline is where dx dt is 0, and you can see that the two horizontal components of the vectors point at each other, which means that once you get to this, the dx dt is 0, and in terms of the y component, we see that on the left-hand side of this y nullcline, all the vectors point up. So even if a point did hit this nullcline, it would travel up and hit that equilibrium point. Pretty cool stuff. Another thing that can happen is, let's imagine that there's a point inside of a different pocket. So let me erase some of these guys. The point starts in here. Where can it go? Well, based on the behavior inside of this pocket, it has to go up and to the right. Now, one possibility is that, well, does it go to the 1-1 equilibrium point? It can't do that because 1-1 is a saddle, and so it can approach 1-1, but it's never going to get there. So one thing that can happen is this point can travel up, and let's see, what happens if it touches that nullcline right there? Well, that's an X nullcline. You can see that below that X nullcline, vectors point to the right. Above that X nullcline, vectors point to the left. On that X nullcline, the vectors only point up or down, and we see that both above and below that nullcline, the vectors point up. So this point can pass into this region like so. Now it's broken through. I guess it would break through more vertically like that, and now this point can either hit that, but either way, it's going to be relegated to go into that equilibrium point. So we have all this power now in determining what is the likely trajectory of that point. Now, another thing that could possibly happen based on the information that we have now is this point goes up and to the right, but breaks into this region. And if it breaks into this region, now it's going to move down and to the right, so it can move and hit this nullcline here. But what happens if it hits this nullcline? Well, that's an X nullcline, meaning it can't pass to the right of that because dx dt is 0 on that green line. And you can see that the right and left arrows point at each other across this green nullcline. And so the only component that we see that's consistent above and below that is the downward pointing arrow. So it would actually be forced back downwards. And perhaps it hits this red line, but this is a Y nullcline, and we see that everywhere below this green line, the vectors point right, so that point is going to have to end up at 2, 0. So some of these points are going to go, that start off in this pocket, may perhaps go to 0, 3. Some of these may go to 2, 0, but it seems to be the case that all of them will have to go to one of those two equilibrium points. How we decide that? Well, I don't think we have total enough information to be able to distinguish between which one these will go to, but we do have more power now knowing that. Now, all initial conditions in here, in this third quadrant region, will all have down and to the left pointing behavior, and we saw this in our phase plane. This is just going to be forced that way. There are no other nullclines there, so since this vector has to travel down and to the left, it will do so indefinitely. And we can kind of make up similar behaviors for all these other pockets as well. Let's go back and look at the phase plane for a moment to see how well this agrees with what we observed earlier. So here we have that phase plane, and we definitely see that what's happening in this bottom left portion, all of those vectors you can see here have a left pointing component and a downward pointing component. So all of these vectors point left and down. Some of them point more down than to the left, like these guys here, and some of them point more left than down. But that's not what this analysis is about. We're just trying to understand the qualities of those trajectories. Now, inside of the other regions, we just determined that, for instance, in this pocket, all of those vectors, notice here, they point to the left and up. But at some point, it appears that some of these points in here, right, they can hit this green line. Now that's an x nullcline. That's where dx dt is 0. So because above and below that x nullcline we see, the vectors point right here, the vectors point left here. The only thing that can happen is if a trajectory hits this green nullcline is both of those arrows point up. So that point will push into here, which is what you see with this wraparound taking place. And I think there's probably some wacky stuff going on here because our step size is too big. There we go. That's a little bit better. And so what actually happens is this point breaks through here. Now all those vectors point up and to the right. And when it hits this y nullcline, we forgot to label the vectors right above here. Those point down as well, since that's to the right of this nullcline. The points kind of come up like this. They break through here, point to the right and up. They hit this y nullcline. The green arrows all suggest that that point's going to go through here. And now that point has to move down and to the right. Well, what if it hits this nullcline? Well, that's an x nullcline. We see that the arrows to the left and right contradict each other, but the downward component faces down, and so that point has to end up there. Such a super powerful analysis that we can gain from this, and we see that happening over here. Down in this pocket, you can kind of see that those points go to 2, 0, and then some of them here, we saw that the arrows over in this region point down and to the left, and that's indeed true. Some of those we said are going to end up at 2, 0, and some of them are going to end up at 0, 3, and you can see that there's sort of this point where those two behaviors vary. And why does that vary so much? Well, it has to do with this 1, 1 equilibrium point, that some of these trajectories come this way but actually pass through like this and make their way up here. And some of those that are just a little bit too low come down and to the left and hit this nullcline and then veer right into the 2, 0 equilibrium point. So we just gained a lot of powerful information from this. And that was all just by looking at signs of vectors, which was a lot more than what we had before. So let's go ahead and take a look at one more example. So now that we have kind of a familiarity with the concepts of nullclines, we're going to perform a similar qualitative analysis for the model proposed below. Specifically, we need to find all equilibrium points, all nullclines, sketch them in a phase plane, and use arrows to describe the trajectory within each bounded region. So here we have our first and second equation. We see that these are definitely nonlinear. We'll have an interaction term, but we also have a squared dependent variable, so that's a big red flag. And we find our equilibrium points by setting both equations equal to 0. We have 4 equilibrium points. In order to know what they are, we have to compute the Jacobian matrix. The Jacobian matrix will be, the top left component will be the derivative with respect to x of this guy, and the top right component will be the derivative with respect to y, which will give us 2 minus 2x and negative x. And the derivative of dy dt with respect to x is negative 2xy, and the derivative of dy dt with respect to y is 2y minus x squared. So I'll just start with the first equilibrium point here, plug that into the Jacobian matrix. I get 16, 2, 16, and 4. And I encourage you to verify all of this, plug it back in, and make sure that you agree. Before we compute eigenvalues of this to classify it, we have to check its determinant and make sure it's not 0. So it comes out to negative 8, which is fine. Now we can compute and proceed to get the eigenvalues, and we see that we get 2 real eigenvalues, which means that the theorem still is valid. One of them is positive, one of them is negative, therefore negative 2, 4 is a saddle point. So trajectories will never end up at the point negative 2, 4 unless they start there. Now 0, 0 gives us this matrix, and the determinant of that is 0, since 2 times 0 minus 0 times 0 is 0, and that's an uh-oh moment. We can't really proceed to find the eigenvalues because we failed part of the theorem, so the theorem is going to be inconclusive. So one thing we can do is to kind of zoom in and see what's going on. And if we look at the phase plane near 0, 0, we really see that the points are moving away from 0, 0, And so it appears that 0, 0 is acting like a source. For the point 1, 1, when we enter that into the Jacobian matrix, we get a determinant of -2, which is fine. Compute its eigenvalues. We get 2 and -1, which means 1, 1 acts like a saddle point. So again, 1, 1 will kind of push trajectories away. We'll kind of suck them in and push them away. And finally, 2, 0 is another equilibrium point, and we get a determinant that is, I think in this case, the determinant of J20 is equal to +8. -2 times -4 minus 0. So we can proceed. The eigenvalues are both negative, and so 2, 0 acts like a sink. Great, so now we're going to find the Nullclines. So the x Nullcline is where dx dt is 0. So all I've done is set dx dt equal to 0, and I get two solutions. I get x equals 0 and y equals 2 minus x. So this is actually, believe it or not, the same Nullclines we came up with in the past problem, but x equals 0 is this vertical line here. 2 minus x is the line that goes through 0, 2 and 2, 0. It's going to look more like that. All right, there we go. And so now we need to, since this is where all the points along these pink vectors, the dx dt component is 0, we need to figure out what's happening along all these intervals. Okay, so that means I need to pick my look at my 4 regions here. I have actually 1, 2, then this region down here, and this region over here. And if I plug those points into my differential equation in each of those 4 regions, and look at the sign of dx dt. Again, the only way for a positive dx dt to change from positive to negative is to jump across one of those Nullclines. So if I pick, let's say in region 1, I pick the point 2, 2, and I plug that into the dx dt equation, which is x times 2 minus x minus y, here I'll get 0 minus 2 times 2, which is a negative value, a -2. So this is going to be a negative value, which means my vectors are going to point left in region 1. So I'll have leftward pointing vectors in region 1. Now in region 2, which we'll just arbitrarily call this region here, I can pick the point 1, 0. And if x is 1 and y is 0, I'll have 1 times 1 is positive 1. And so the vectors in region 2 are all going to point to the right. So that's up here and here as well, because that's not a Nullcline, that's just an axis. Region 3, if I pick something over here, say -1, 0, that will come out to be negative, which means those vectors will point left. And region 4, which is here, if I pick something like 1, 1, 4, then that will be a positive value, and those vectors will point to the right. So here all the vectors point to the left, here all the vectors point to the right. I'm going to repeat this analysis. This is just my x Nullcline. I'm going to do my y Nullcline analysis now. So set dy dt equal to 0, and we see that we have two positions, or two places where that happens. Y equals 0, which is the horizontal line here, and y equals x squared. Now y equals x squared is actually a parabolic function, so we'll plot some points on this, -1, 1, and 1, 1, and then 2, 4, and -2, 4. So we kind of have something that looks like this, a parabola here, and that's going to work just fine. Okay, so we have, again, 4 pockets. We have this pocket, this pocket, this pocket, and everything below the horizontal axis. Again, we know that along the pink curves, anywhere along there, dy dt is 0. So if you pass through a Nullcline, then you can only pass through horizontally, not vertically. And so, okay, once again, we're going to pick points in each of these 4 regions and figure out whether dy dt is positive or negative in those regions. So here's region 1. I could pick something like 0, 1, which is in that region. And if I have 1 for y and 0 for x, that's going to give me a positive number. And so this is going to be positive, which means the vectors point up everywhere above here. Now I'll pick another point, like let's say 2, 1. And at 2, 1, if I plug those points in, I'm going to get a negative slope. Again, I've done the work on this already to save some of that time. And that's, we'll call that region 2. So all the points in region 2 will have downward vectors. And then region 3 is down here, so we'll actually end up picking a point like 0, negative 1, which is this point here. And if I choose that, then I'm going to get a positive, I think. Let's see, 0, negative 1 for y. I'll get a positive value. So this will give me a positive, which means all the vectors will point up. Or the y component of the vectors will point up. And that's region 3. Region 4 is over here, so let's pick negative 2, 1. Negative 2, 1. And that's going to give me a negative slope, and so those vectors are going to point downwards. Now I'm going to put these two things together now and draw all the x and y nullclines together on the same graph. So let me go ahead and do that below. And so here we have just a copy of that x nullcline graph. It just helps to superimpose your work on one that you've already drawn. So I encourage you in these notes just to go ahead and draw on top, put the x nullclines on top of the y nullcline graph. And so all I'm going to do here is just go ahead and reproduce this component here like that, and also this component down here like so. And now all I have to do is just transfer all of my green vectors across those different regions of that pink line. So remember, everywhere to the top right, those vectors all have left-facing components. So that's also here, because again, we're within that region, the top right region, and same thing down here, that's going to point right. Now, as long as we are in this pocket here, the vectors all point to the right. If we're in this pocket here, we're in the region that's below the two green intersecting lines, and those vectors will all point, left. Those vectors will all point left because of this vector here. Now, if we're inside of this triangular region here, everywhere within that triangular region, the vectors point right. So right there and right there. So we have that all labeled. Now we have to get the pink components to see whether there's going to be up or down travel. If we're within this region 2 of the y nullclines, those vectors are all going to point down. So that's going to be everywhere inside of this region. So here and here. Now if we're within that parabolic region, above that parabola, all of those vectors point upwards because that's region 1. So we're going to attach upward components to all of these vectors in there. And then within this pocket, we said they all face down. Within this region, they all face up. And same thing here. That's upward because that is below. And we see that we have this all pretty well labeled. And we again see our equilibrium points. There's 1, 1. 1, 1 we said acts as a 1, 1 acts like a saddle point. 2, 0 acts like a sink. 0, 0 acts like a source. So only 2, 0 can actually suck solutions into it. 2, 0. And again, we can just see where these equilibrium points are, where the green and pink lines intersect. There's 0, 0. And we have one more at negative 2, 4, which is this point here. So we have another equilibrium. So that's a saddle. This is a saddle. This is a source, and this is a sink. So solutions can arrive at 2, 0. Let's take a look at a sample trajectory. So what might a sample trajectory look like? Well, what about a particle that starts in here? Where will it go? Well, it's going to go down and to the left. So one possibility is this point comes here and bumps into this Nullcline. Well, that's an X Nullcline, and you can see that to the right of that X Nullcline, vectors point left. To the left of that Nullcline, vectors point right. So there's a contradiction. That means dx dt is 0 at that point. But we see that the arrows have downward facing components. So this point will kind of break through vertically into here. And now that vector has to travel down and to the right. Well, it could come into the equilibrium point 2, 0, like so, because it's a sink. It also could actually maybe hit this pink Nullcline. But that's a y Nullcline. That's where dy dt is 0, and you see that there's a conflicting downward and upward pointing arrow. So that point cannot break into this region because it's a y Nullcline, no incline. But we're on the right-hand facing side of the x Nullcline, so this point will have to come into 2, 0. Now another possibility, of course, is that that point comes in and hits this Nullcline first. That's a y Nullcline. You see arrows point down below this, and they point up above this. So since it's a y Nullcline, that means this point cannot go upward, but all the dx dt say that it will point right, so it'll break through there. Now this point is forced to go up and to the left, so it could go up and to the left forever. Or perhaps what happens is it hits the green Nullcline, and if it hits the green Nullcline, well, that's an x Nullcline, so dx dt is 0, and we see that both of the y components face up, so this point is going to veer off to infinity, either like that or like this guy here. And a point that starts, say, inside of these regions, like, let's say something that starts near 0, 0, like say here, that point is going to move up and to the right, so the one possibility is, well, it can't hit 1, 1 because 1, 1's a saddle point. It can come closer to it like this, going up and to the right. It's got to hit that Nullcline. That's an x Nullcline, which means you see there's a leftward pointing arrow to the left of it, or rightward pointing arrow to the left of it, and a left pointing arrow to the right of it, which means the only way to pass through this is to go straight up into this region. And we already know what's going to happen here. That point's going to go off either to infinity like that, or off to infinity like that. And so all those points are just going to have an infinitely growing y component. Let's go ahead and take a look at the phase plane real quick, just to see how this behavior actually comes about, or how it looks in that phase plane. So in here we have it. We can kind of see that we said that a point that starts over here is going to be relegated to hitting that 2, 0 equilibrium point. You can see that the x versus t, x hits a value of 2 and stays there, y drops down to a value of 0 and stays there for all time, and all of these points seem to go to that same equilibrium point until you get above this parabola, which if we look at the point 1, 1, which is somewhere right there, we see that all those points are going up towards infinity like we described. And kind of what's going on in here, these points will go down and to the left, and those points will go out forever, because if this point hits this Nullcline, that's where dy dt is 0. Both arrows point left, therefore that point should go out infinitely in that direction as well. And down in here, you can see those points are going up and to the right, so likely they're going to hit 2, 0, and you see that they all do. These go to the left and up, and so everything that happens down here has to go to the equilibrium point 2, 0. Now we also have this little pocket here, and we said that if you're really close to 0 but below that parabola, you can see that that also hits the equilibrium point 2, 0. So what we've done here in this video, to recap, is a Null-Cline analysis. It's a way of visualizing what's going on in the phase plane and to understand what trajectories or what paths certain initial conditions may take just based on analyzing the rate of change equations. Notice that we didn't do a lot of heavy calculus. We just had to compute some vectors, and we were able to map out pretty accurately what's going on everywhere in that phase plane. So this is a very useful tool for homogeneous nonlinear systems.